Geometry. My name is Cyril Goldstone. I teach at Blobergrant High School, and I'm very happy to be with you this afternoon. Now, as you know, Euclidean geometry has come a long way for us in mathematics. Euclid was a Greek mathematician who lived in the year 300 before our common era. That's 300 BCE. And what he thought about, in line with his contemporaries, in terms of structures, buildings, laws, principles, have all come down to us today. And we have the wonderful privilege of entering into this elevated thinking by means of Euclidean geometry. Now, I just want to say that many learners always say, oh, I don't like Euclidean geometry. Oh, that's one section of the maths paper 2 that I really don't like. I just don't get it, they say. Grade 12s, in paper 2, Euclidean geometry is worth 50 marks. Remember, trigonometry is only 40. Euclidean is 50 out of 150. So it's a third of your paper. And what is examined in grade 12 takes you right back to grade 10, one can really say. In fact, your whole high school career, for that matter. And you'll see in our program this afternoon why I say that. Because we start examining theorems. We start looking at mathematical principles that play off in connection with Euclidean geometry. And so it's so important that for every statement that we make, we must have a concrete reason. That's the bedrock of our understanding and our approach in connection with Euclidean geometry. So what are we going to explore this afternoon? Let's have a look at some of the acceptable reasons that you've come to know. You may recall that there is a theorem that states that the line drawn from the center of a circle perpendicular to a chord bisects the chord. And then there's a theorem that also states that the line from the center of the circle to the midpoint of the chord is the perpendicular bisector as well. The angle at the center of the circle is equal to twice the angle at the circumference. The angle in a semicircle is equal to 90 degrees. And of course, we know that there's a diameter that's involved there. The angles in the same segment are angles that are subtended by the same chord. Equal chords and equal angles, another important reason in connection with Euclidean geometry. The opposite angles of a cyclic quadrilateral are supplementary. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. The tangent is perpendicular to the radius. This also plays off in analytical geometry as well. It's a fine mathematical principle. Tangents drawn from a common point are equal in length. And the tan chord theorem states that the angle between a tangent and a chord is equal to the angle in the alternate segment. This is a synopsis of some of the main reasons that are used in Euclidean geometry. And you'll notice in our program this afternoon how these reasons, acceptable as they are, form the basis for our calculations and our reasoning as well. So, first and foremost, let's examine the center of the circle. Let's start right in the center. As you can see on the monitor, there are various diagrams that show the center of the circle. And if we pull them all up, right here, we see some very interesting concepts. Here we have the center O. Now the line drawn from the center of the circle, perpendicular to the chord, bisects the chord. So in other words, AM in this diagram is equal to MB, right? As well as it gives rise to a 90-degree angle. Don't forget that. And then have a look at this. In this diagram here, not only is this line, which is the radius, drawn to the other side of the circle, that's why it's a radius. This is a chord, you remember that? Because it's going from one side of the circle to another side, but a radius is from the center to the circle itself. There's another radius there. So these two radii, when added together, form a diameter. There we have this diameter here. And it looks like this line is extended, so in a very real sense, we can actually say this is a secant too, because it's cutting the circle there as well. Have a look at this. The angle at the center of the circle, there's our 2x, is twice the angle at the circumference. So that angle there is x, therefore this one must be 2x. Here we have a diameter in red, Notice there's the angle in a semicircle. That's 90 degrees. And there's another one here, 90 degrees. Notice these two are angles in the same segment. They are subtended by this chord here. And that would make this figure a cyclic quadrilateral. Then we have interesting situations here where this part of the circle equals that part of the circle. This is equal to that, and these two are vertically opposite, as we've seen. Now, let's have a look at cyclic quadrilaterals. You may remember in grade 11, when your maths teacher first introduced this, you probably thought to yourself, I don't know how on earth am I ever going to remember cyclic quadrilaterals. And the more question papers you look through, the more textbooks you look through, the more you saw this scary term, cyclic quadrilateral. Ooh. Well, grade 12s, it's not that scary at all. As a matter of fact, the cyclic quad is one of our friends in Euclidean geometry. I love Euclidean geometry. It is so interesting. It's so interesting. It's so logical. It's so fascinating. And therefore, we can enjoy that part of the exam paper as well. Getting back to the cyclic quadrilateral. For any quadrilateral to qualify as a cyclic quad, there are just three main conditions that must be met. Any one of the following three. Number one, the opposite angles of a cyclic quadrilateral are supplementary. In other words, the opposite angles of a cyclic quadrilateral, when you add them up, they equal 180 degrees. If that's the case, that's a cyclic quadrilateral. Point number two, the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. If you find an exterior angle, and here's a little tip. Whenever a question says that a certain line is produced to a certain point, that's an indication that there is an exterior angle that has just been created right there. So remember that word produced means exterior angle. Look out for that. And if the exterior angle is equal to the interior opposite angle, it's a cyclic quadrilateral. Thirdly, angles in the same segment. When angles are subtended by the same chord, that is the third reason for a cyclic quadrilateral. Of course, those angles are equal. Angles in the same segment, they're equal, and they subtend by the same chord, so there we go. To summarize, 3 points in connection with the cyclic quad. Number one, the opposite angles of a cyclic quadrilateral are supplementary. Number two, the exterior angle of a cyclic quad is equal to its interior opposite angle in magnitude. And number three, angles in the same segment. In other words, angles subtended by the same chord. And we'll see how that plays off in our discussion this afternoon. And so looking at it diagrammatically now that we've heard all of that vocally, let's have a look at the diagrams that play off in this connection here. Well, have a look at this diagram here. There we see angles that are subtended by the chord. Which chord is subtending them? It's this chord CB. It subtends this angle and that angle. Here's another chord here. Don't forget that right here. There's another chord, and that chord is subtending this angle that's marked A and that angle A there. Do you notice that? That means that this figure here is a cyclic quadrilateral. Have a look at this figure here. There we have some interesting. There we see this angle equal to that angle. Once again, the subtended. Notice this line segment is equal to that line segment. And now, coming to another point in connection with our cyclic quads, you remember the first point? If angle X plus angle Y equal 180 degrees, maybe angle X is 80 degrees, for example, and angle Y is 100 degrees. Because they add up to 180 degrees, this figure here qualifies as a cyclic quadrilateral. And then if you look at this diagram here, why, there you have an exterior angle here, and it's equal to the interior opposite angle there. So those 3 points in connection with cyclic quadrilaterals are what are very important. In Euclidean geometry, what is also very important to remember and to capture in terms of one's thinking are our tangent theorems. So let's have a look at them now. The tangent theorems are important for us, right? And there we see a summary of all of them. Let's first have a look at this one. Here we have a tangent. Remember, the tangent, these are very touchy things. They just touch the circle, right? Tangent perpendicular to the radius. When a tangent meets a radius, The angle that is created is a 90-degree angle or a right angle. Then if we go down here, you have a tangent to the circle and another tangent to a circle here. Well, these tangents drawn from a common point are equal in length, and we'll notice how that plays off in our calculations. And then here, arguably, one of the famous Euclidean geometry theorems. The angle between a tangent and a chord is equal to the angle in the alternate segment. There's your tangent, there's your chord, and there's your alternate segment. Can you see that? This angle here is equal to that angle here. But this tangent extends. Notice it keeps going this way. So this is also part of the tangent. This one here, you see with the two lines, there's the chord is equal to that angle there. So be on the lookout for that. Grade 12s, you may be saying, so now how do I perfect the skill of all of this? Simple. Practice, practice, practice. The more exercises you do in connection with working through questions in textbooks, study guides, as well as past exam papers, the more your skill in handling riders, that's what these questions in Euclidean geometry are called, riders, the more your skill in solving riders becomes. All you'll have to do is learn your theorems. Once you know your theorems, you can then apply what you've learned in your theorems to each rider, and you'll see how things work all very nicely. Now, moving forward, let's go back to cyclic quadrilaterals, and let's just have a look at a situation that is sketched here. Remember I said that there are three important reasons, right, or three important conditions for something to be a cyclic quadrilateral. Here's our first one. Angle X plus angle Y must equal 180 degrees, right? And of course, there we see it here in its diagrammatic format. Look at this one here. These are angles in the same segment. In terms of a circle, there we see them play off there as well. So here we've got two conditions mentioned. The opposite angles of a cyclic quadrilateral are supplementary, and here we have angles in the same segment. If we move on with that, well, then we have this situation. There's our third condition. The exterior angle of a cyclic quadrilateral is equal to its interior opposite angle, and we see it clearly sketched here in the diagram. So, moving forward, when we bring all of this together, we notice how all of this plays off in connection with cyclic quadrilaterals, in connection with tangents. This forms the bedrock of our Euclidean geometry. What we want to do now is we want to have a look at an example, a question that occurs in the source material, right? And see how we can really solve this particular rider. Now, grade 12s, there's a motto that I always teach my learners. In fact, this is the motto by means of which I live. Even my WhatsApp status has this motto. The motto is, plan your work, then work your plan. And many, many years ago, a teacher who taught maths to me in primary school helped us appreciate that if we live by a principle like that, we can go very far in life. I want to pass that on to you today. Plan your work, then work your plan. You see, in Euclidean geometry, what I find very, very helpful is to plan your work by using these highlighters. And you'll notice, in connection with what we're going to explore now, how we're going to make very good use of our highlighters to solve this particular rider. Now, you see it on the monitor. Let's go into this. It's in your material, and it's drawn from an interesting question paper. You'll notice that it's drawn from the Department of Basic Education's paper, February and March 2015. So that was a supplementary exam paper. All right, 2015. That is an important point because, if you want to check out the memorandum later on, which is very good for different options in connection with solutions, it's always nice to know where we can find that. And that's important because we want to leave you with the skills of self-directed learning. It's important, grade 12s, that you become motivated on your own to study and also start teaching yourself in connection with important concepts in terms of mathematics as well as your other subjects. Remember, when you go to a tertiary institution, you will need this skill of self-directed learning. And regardless of what comes our way in terms of another virus, pandemic, or whatever the case may be, you'll be able to cope very well because you have the principles of self-directed learning firmly in place as well. Coming back to this question, let's explore. The question says, in the diagram below, the circle with center O, so there's the center right here, right, passes through A, B, C, and D. They tell us that AB is parallel to DC. So what I find very good is to mark my parallel lines. They've done it, but let me put it in a color so that I can see these are parallel lines. Now, we know lots about parallel lines, right? Parallel lines give rise to angles that we can really use. For example, alternate angles are equal because two lines are parallel. Corresponding angles become equal because lines are parallel, and so on and so forth. So when a question says this line is parallel to that line, we look out for alternate angles, corresponding angles, and all other angles that link to parallel lines playing off very nicely for us. Then they give us a magnitude of an angle, which is interesting because we obviously will have to calculate other things. They tell us that angle BOC is 110 degrees. And there it's clearly marked on the diagram. But what I'd like to do now is I take my highlighter and I mark this right here. 110 degrees. Right? There we have it right here. Now, grade 12s, we've got a lot. They further tell us the chords AC and BD. AC and BD intersect at E. That's the point of intersection. EO, there's EO. BO, there we have it. CO and BC are joined, right? So we can say there are no lines just floating around in that circle, in a sense. What is also very interesting to note, right, which by implication has been stated. Notice the question said, or the opening statement said, that O is the center of the circle. There it says it right here. O is the center of the circle. That means that BO is a radius as well as OC is a radius. In other words, what I'm saying is these two lines are equal, right? And therefore, at the base of these lines, we have equal angles because the lines are equal as well. But we don't want to run ahead too much. We want to see what the question is actually asking us to solve. The question says, now, as you can see on the monitor and also in your material there, calculate the size of the following angles, giving reasons for your answers, right? The size. Now they say we must find angle D. This one here. Let me highlight it here. Angle D. There it is. I put a green dot there. Well, immediately I say, well, you know what? The theorem states that the angle at the center of the circle is twice the angle at the circumference. So if I have to write this down now, I'll say the following. That angle D, right, and I can put it like that, is equal to a half of angle BOC. Angle BOC, right? There's angle BOC. I marked it in pink there. And that is a half. BOC, I know, is 110 degrees. And that gives me an answer of 55 degrees. So angle D, I know, is equal to 55 degrees. Here's my ruler. Let me underline this as my answer because I know that I've got my marks. However, there's something that I haven't done. And that is what the question has asked me to do. The question says, calculate the size of the following angles, giving reasons for your answer. So now I need to go right back here. Angle D is equal to half of angle BOC. What is my reason? I can simply write the angle at the center, right? The abbreviation that's acceptable is found in the examination guidelines, is equal to twice times the angle at the circumference, or at the circle for that matter, right? Like that. That's my reason. And there I get my marks. That's 2 marks, right? Remember, statement and reason. Very, very important. The next one, 8.1.2 says, I must find angle A. So what I need to do now is, because I found D, what is very good to do is immediately write that in on the diagram. So here now, I'm going to put this as 55 degrees. I'm going to show that, 55 degrees, because that's going to help me in my calculation. The next part of the question says, I must find angle A. Oh, angle A is there. Now, that's very, very interesting. You see, angle A is also at the circumference. So in a very real sense, what I need to write here is angle A is equal to a half of angle BOC. Once again, same situation, right? And the reason for that, angle at the center of the circle is equal to twice the angle at the circumference, right? And then I know the magnitude of BOC, like I had in the previous one. It's also 110. It's the same angle I was talking about. Angle A is equal to 55 degrees as well, right? So we've got that. Now we have an interesting situation here, right? If you notice the diagram, right? If you look at the monitor, there on the diagram, there's angle A, this is 55 degrees. There's angle D, that's also 55 degrees. Very, very interesting. You see, because both of them, right, are angles at the circle, at the circumference, and there's the angle at the center of the circle right here. Okay, fine. Now we are asked to find angle E2. So when we look at our diagram, let me put that aside, angle E2. If you look at our diagram, here's angle E2 here. There we go. Right here. There's angle E2 there. Oh dear. Now we think to ourselves, now how do I find E2? Well, notice how we write that. If you look at your diagram very carefully, let's write this down. Let's start with angle B1. Angle B1, right? Angle B1 is equal to angle D, and that's equal to 55 degrees. Look carefully at your diagram. Are you looking at your diagram? We're saying angle B1 is equal to angle D, right? And that's equal to 55 degrees. Remember, we found angle D. And the reason for that is they are alternate angles. And we don't stop there. We must name the lines that are parallel. AB is parallel to DC. That's it. We got that? So angle B1 is equal to angle D, and that's equal to 55 degrees because they are alternate angles, and they are alternate because AB is parallel to DC. Continuing this now, very important. Our next step is now angle E2. That's the one in question. We need to find him. Angle E2 is equal to angle B1, if you look at your diagram, plus angle A. All right? Look at that. Here, if we look at our diagram, angle E2 is equal to angle B1 plus angle A. You may be saying, yes, but now how come? Well, you remember in grade 8, in grade 9, you learned very nicely that the exterior angle of a triangle is equal to the sum of the interior opposite angles. So we write that down. That's the exterior angle, right? Exterior angle of a triangle. And that is equal to the sum of the opposite angles. That's what we do. Right. So we've got that down. Now let's populate it. Do we know the measure of angle B1? Oh, yes, we do. Angle B1, as we know, is 55 degrees. That's 55 degrees. Do we know the measure of angle A? Yes, we found angle A in the previous step, plus 55 degrees. And that's equal to, we add that up, angle E2 is 110 degrees. Right? There we found that very, very nicely. So that's how we find the measure of angle E2. Now the third part of the question, if we look right at the bottom, the 8.2, notice angle 8.2 says, prove that BEOC is a cyclic quadrilateral. That's BEOC is a cyclic quadrilateral. Grade 12s. Do you remember we've established for something to qualify as a cyclic quadrilateral, any one of the following should obtain. Number one, the opposite angles of a cyclic quadrilateral are supplementary. 2, the exterior angle is equal to the interior opposite angle in a cyclic quadrilateral. And point number 3, angles in the same segment. Well, let's look at our diagram now on the monitor and let's see what we've got. You see, if we're going to find that this is a cyclic quad, very easy. Have you noticed that angle E2, which is what we've just found, right, is equal to angle O1, and that's equal to 110 degrees, right? We know that. We found that. We don't have to even give a reason. We can just say proved above or something like that, right? Proven in, 8.1.3. Let's just say, if we're going to give a concrete reason, that's fine. That's a nice reason. And therefore, if that's the case, look at E2. There's E2 there. There's E2, and there's a 1. They are subtended by this chord BC that makes BEOC a cyclic quadrilateral. So therefore we say, therefore BEOC is a cyclic quadrilateral. I'm just going to say cyclic quad for short, right? And we know the reason for this is equal angles subtended by a line. Right? There we go. And there we proved it. Did you notice how we could easily solve this? We had to know our theorems. We had to know the relationship of angles linked to those theorems as well. Notice how easy this becomes. Notice how things fall into place. How from the center of the circle, we're given just one angle, but we can find the angle at the circle. We can find angles that are subtended. We can actually prove that certain figures in a circle are cyclic quadrilaterals. Very, very important. This is the beauty of Euclidean geometry. Now, moving on with our revision program, we now come to another important section, proportionality and similarity. We need to talk about this because this is linked in a great way to everything that we do in Euclidean geometry. In fact, it's a major part of the final section of Mathematics Paper 2, which is generally written here in South Africa on a Monday. Paper 1 being written on a Friday. In connection with proportionality and similarity, Euclid, as well as other great thinkers, found that triangles can be in proportion. They can be similar, and yet not equal in length. There are certain things, their angles could be equal, but their sides necessarily are not equal. You could have a small triangle and a large triangle. They're similar by virtue of the fact that their angles are equal. And so we need to have a look at this in review. If you notice the monitor, there we have our proportionality theorem. I encourage you, grade 12s, to learn this off by heart. A line drawn parallel to one side of a triangle divides the other two sides proportionally. And there you're given the diagram. As you can see, a diagram, a triangle. And there you have two parallel lines there. There's your large triangle. There you have your line DE and BC. These lines are parallel. That now is known as the proportionality theorem. Once again, a line drawn parallel to one side of a triangle divides the other two sides proportionally. So how do we write that out? Well, you can write it out like this. Proportionality theorem, semicolon, DE parallel to BC. We see it clearly sketched in the diagram here. Now, if DE is parallel to BC, then we know the following, that AB over DB is equal to AE over AC. Do you notice that important flow from the proportionality theorem? As well as AB, that's the long blue one, as you can see here, there's AB. AB over AD will be equal to AC over AE. These are all important points that flow from the proportionality theorem. As we mentioned, there we have our AB over AD. That's equal to AC over AE. All very, very important. And as we go on and on, we can populate this over and over by having a look at all of these. Now, we need that knowledge for certain calculations that we basically do. Here's an easy calculation, an easy example, right? We're not going to do this one because it's so simple. If you have a look at this, the question says, in the diagram below, triangle ABC. So there we have our triangle. ABC has D on AB and E on AC, so that DE is parallel to BC. So we know the proportionality theorem is at work here. They then tell us that DB is 2 units. DB, here it is, 2 units. EC on this side is 3 units. AD is X, and AE is X plus 2. Determine the value of X. Now, there are many ways to do this. We can say AD over AB is equal to AE over AC. proportionality theorem, that's our reason, semicolon, DE is parallel to BC. And then we work out that. I encourage you to work out that answer. It's easy. Let's get on to more complicated things. Let's have a look at the converse of the proportionality theorem. The converse states, if a line divides two sides of a triangle in the same proportion, then the line is parallel to the third side. Notice, if a line divides two sides of a triangle in the same proportion, then the line is parallel to the third side. And the abbreviation that's accepted is line divides two sides of a triangle in prop. The prop means proportion, right? And there we have it, nicely sketched for us. And that is the converse of the proportionality theorem, right? In other words, because those lines, right, are in proportion, now here we have these parallel lines as is indicated on the monitor. Also, everybody, we need to make the clear distinction between similarity and congruency. Now, oftentimes, this can be one of the biggest traps in an exam. Remember, for congruency, right? And the definition of congruency is that two triangles are equal in every single respect. Congruency has the mathematical sign that looks like that, right? That's congruency, three lines like that, okay? There we are. These two triangles are congruent. Whereas similarity goes the other way. Similarity is this way here. Right. Have you got that distinction? These represent congruency, right? This represents similarity. So when two triangles are similar, this is the sign that will come between them. Triangle ABC is similar to triangle DEF. But when two triangles are congruent, triangle ABC is congruent to triangle DEF. Now, let's notice this. In connection with similarity, on the monitor we see, if two triangles are equiangular, right? We're talking about similarity now. Then these triangles are similar. For equiangular triangles, we use the reason angle, angle, angle. And when two triangles are similar, their sides are now in proportion. Did you notice, grade 12s, if you're going to prove similarity, your final step should involve a situation that looks like this. The one triangle is similar to the other triangle, and in brackets, angle, angle, angle. And then as is mentioned here, now we have to take their sides in proportion as well. So, for congruency, notice now, you may remember this from grade 8 and grade 9, right? There are four conditions for congruency. One triangle congruent to the other triangle. Here are the four conditions for congruency. It's either side, 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 or side, angle, or angle, angle, side, or 90 degrees, hypotenuse, and side. Some conditions for that fourth one say right angle, hypotenuse, and side, right? Makes the same, it's the same thing. 90 degrees, right angle, it's one and the same thing, right? So here we have the four conditions for congruency. We must not confuse congruency with similarity. Do not confuse congruency with similarity. Make sure that you know what is being called for. So moving forward now, when we have theorem 2 in connection with proportionality, we have the following. If two triangles are equiangular, then the corresponding sides are in proportion, and consequently, the triangles are similar. There we have how that is written. So, if we have a look at these two diagrams, here we see something very interesting. Here's this larger triangle, ABC, and here's a smaller triangle, EDF. Notice angle A is equal to angle D, angle B is equal to angle E, angle C is equal to angle F, right? What does this mean? If two triangles are equiangular, there we see it clearly, the equiangular, then the corresponding sides are in proportion, right? And that's the designation that we use there. So, what does that literally mean for us? Well, the final countdown means that this is a situation that will obtain because those triangles are similar and they are equiangular as well. Now, in the source material, there are a number of questions that are dealt with, and here's an example, right? Very nice question. In the diagram, ADE is a triangle having BC parallel to ED and AE parallel to GF. Also given, as you can see there, is that AB is to BE in the ratio 1:3. So now we're introducing the ratio concept. They also tell us that AC has got 3 units in length, and EF is 6 units in length. Very important. Now, CG is X units in length, and we have to find our CG. How do we go about this, grade 12s? We use the principles of similarity and proportion, right? We have parallel lines, so we can play around with all of this. Generally speaking, this is one of the easier examples. Let's go to our final example, which we are going to explore. And it's this question here, which was drawn from the March 2016 paper. I'll work through this one with you, and we'll see how all of this really plays off nicely. The March 2016 paper, as you can see, there in the corner there. Here we have our reference. So in case you want to check it out later on, there we have it right there, March 2016. And there on the monitor we read, in the diagram below, triangle ABC, so that's the large triangle, and triangle PQR are given with angle A. And now what's very good to do on your own examination booklet, the question paper, highlight these. So there's our angle A, so I'm going to put a pink dot here. That's equal to angle P, right? And then I'm going to take angle B, which is this one here. I'm going to highlight that. That's equal to angle Q right here. And then angle C, which is this one here, we are told that's equal to angle R, right? So now at least things stand out and it starts making more sense. I'm also told here that DE is drawn such that AD is equal to PQ. So in other words, if I have to take this here now, this one here is equal to this one here, right? And then AE, which is on the other side, there's 2 of them here, that's equal to this one here, which is lovely, really nice. Now the question says, question 10.1.1, prove that, so we must work to that proof, that triangle ADE, so if you look at the monitor there, there's our triangle ADE. Prove that this triangle ADE is congruent, notice, not similar, but congruent to this triangle here, right, congruent. And there they give us 2 marks. Now, let's work through this proof very quickly, all right? Firstly, we start by saying, in triangle ADE and triangle PQR, because that's what they said we must actually, those are the triangles they said we should focus on. Point number 1, right? If you look at triangle ADE and PQR, point number 1, they give us a side. AD is equal to PQ. You agree with that? Right, so let's write that down. So that's AD is equal to PQ, right? And we can say that that's part of the construction, right? That's the reason we can give. It's part of the construction, which we will have to do, right? And which has been done there as well, all right? Now, second point, look at those 2 triangles. Did you notice that the pink and the pink are in each of those triangles? Yes, you got it. Angle A is equal to angle P. And the reason for that is simply given. All right? They gave us that. And then thirdly, look at the blue. AE is equal to PR. Right. So 1, 2, 3. We have here AE is equal to PR. And the reason for that is construction, which is also given as well. No problem. All right. There we go. We've got 3 concrete points. What is the net effect of all of this? Well, therefore, triangle from the top, ADE, is congruent, notice how we write that, to triangle PQR. And look at this, grade 12s, side, angle, side. We put the condition on the side here. Side, angle, side. There we have it. Right? That's how we solve this particular part of the rider. Now, with that in mind, we know that those are congruent. Let's go further. 10.1.2 says, now, we look at our diagram. You can see it on the monitor. Even here, they say we must prove that DE is parallel to BC. Oh, that's interesting. That looks like a bit of the proportionality theorem. DE is parallel to BC. Well, keep looking at your diagram on the monitor there. Let's start by saying, well, angle ADE is equal to angle Q. And the reason for that, triangles are congruent, we can say, and these two angles are corresponding angles, right? Corresponding angles. They are corresponding angles of that. Now let's look at our diagram just to crystallize this. Notice we said that ADE. In other words, what we're saying now, if we have to take a color here, this one here, right, is equal to this one here, right? So there we're saying angle ADE is equal to angle Q. Now that's a very interesting one because they are corresponding angles of two triangles that are congruent. Now that's very interesting. But we know, angle B is equal to angle Q. How do we know that? There's our reason. We are given that. Let's just see what we've been saying. We go back to our diagram. There we have it. Angle B is equal to angle Q, right? Angle B is equal to angle Q. So the logical deduction now that we can make is therefore angle ADE must be equal to angle B. And if that's the case, therefore DE is parallel to BC. And the reason for that is corresponding angles. There we have it. All right? Simply put. Have we got that? Notice angle D, this ADE, is equal to this angle B. These are corresponding angles, which makes this line here parallel to this line here. And once you find that out, once you prove it, now grade 12s, put it on your diagram so that it all plays off very nicely. Notice how colorful, just looking at this diagram, looks like jelly tots all there, right? How colorful this really is because it starts to make sense. Finally, we need to do 10.1.3. Now that's easy. After we've done all of that, 10.1.3 says we must prove. Notice it says hence. Now in mathematics, the word hence means from what has come before. Take it one step further. So the question says, if you look carefully now, hence prove that AB over PQ is equal to AC over PR. Well, we start this way. We say AB, as you can see from our diagram there, over AD is equal to AC over AE. And our reason there is proportionality theorem. DE parallel to BC. Right, let's just take it again, looking at our diagram once again. We're saying AB, so now what we're saying is we're taking this guy here, AB over AD, and we know this should equal AC over AE. Right, there we go. Now, the next step is but. We know there are two lines that are equal. AD is equal to PQ and AE is equal to PR, right? Therefore, if we take now that and substitute it, AB, going back here, that was AD, we put PQ here. That should be equal to AC over, and we put there, PR. Because there we have this one there, and there we have that, and that's how we find it, right? Very, very important. What have we been saying in our program this afternoon, grade 12s? Here are the main points in connection with Euclidean geometry. Please have a look at the monitor. When it comes to time management, work through past question papers. Use your mark allocation as a guide as to how much time to spend on each question. Remember that mathematics requires knowledge and skill as well. Both of them, it's a combination of that. So therefore, as shown on the monitor, practice, practice, practice. Remember, practice builds self-confidence in answering exam-type questions. And in everything we do, let's remember, if we have a little bit of practice, we're going to get fewer marks. But if we have more practice, if we work through lots of papers, we're going to get more marks. So let's remember, in everything we do, let's plan our work, work our plan. Euclidean geometry is one of the most fascinating features of mathematics. All the best grade 12s as you accelerate your efforts in gaining skill in working through past Euclidean geometry riders. Bye-bye.